This is a video on statistics. What I'll be talking about today are all the different ways of describing data. So often we call this descriptive statistics. So we'll look at statistics, which are the numbers you can get from data. We'll also look at charts and graphs. So we'll start out with measures of the center. That'll be the mean and the median and the mode. Then we'll look at the measures of the spread. The main one we'll look at is the standard deviation. Then we'll look at measures of relative standing. That's going to be the first quartile and the third quartile and the interquartile range and percentiles. Then I'll look at histograms. Then we'll look at other charts, such as stem and leaf plot, or box and whiskers plot, Pareto diagrams, and a bunch of other charts. So let's go right to measures of the center. I'm going to start out with the big one, and that's the mean. So the mean, you all know, at least you know it as the average. And the average means add them all up and divide by the total. A big part of this class is having a population and then saying we can't get all the values, so instead we're going to take a sample. So the population mean we will denote by this Greek letter mu. And the formula for that is add them all up. This sigma from math means add them up. X are all the data values. And then 1 over n means divide by n is the total number in the population. And we typically use a capital N for that total number. On the other hand, the sample mean, we're going to use this right here. That's x with a bar over it. And the fancy way of saying that is x bar. And it has the same formula. We add up all the data values. But in this case, instead of dividing by capital N, we divide by little n, because we know the sample size instead of the population size for the data. So that's the mean. And again, you've worked with the average before, so I'm not going to spend a lot of time kind of explaining what the average means. I'm going to assume you know that. Similarly, the median and the mode, you've had that since grade school. The median, just a reminder, is the middle number from the data, or if there's an even number of values, we take the mean of the middle two numbers. So when should you use the median and when should you use the mean? Well, the median is often used for home prices or income or birth weight. So one of the things that these have in common, so for example, in my town of Tahoe, most of the houses tend to be between $250,000 and $600,000. But then you have those beautiful mansions that have lakefront property that go for $15 million. If you took the mean, you'd end up with a mean that is nowhere near any of the houses in value. It might be $1 million for the mean, and that doesn't represent anything, really. It doesn't represent the typical house, which is like where I live, in that $250,000 to $600,000 range. It also doesn't represent the mansions. It's not that useful when you want to represent a typical house. On the other hand, the median will give you what a typical house is like. And that's more like where I live, in a neighborhood, not on the lake with this big mansion. Income is the same idea. If you look at a standard business, for example, most people make somewhere between, I don't know, $10 and $30 an hour. But then there's a CEO, the owner of the company, who might be making millions of dollars a year. And if you took the average, that's not going to represent the regular person who works at the company, because the CEO of the company is making so much that CEO is an outlier, which skews the data or skews the mean upwards. The median, on the other hand, will represent the typical worker at the company. We could also talk about the mode. The mode is just the value or the values that occur the most frequently. So let's move on to measures of the spread. So the big one is called the standard deviation. The standard deviation is a measure of the spread of the data, and it's kind of an average of how far the data values are from the mean. We could talk about the sample standard deviation, which we'll use the letter S for, lowercase s. I don't expect you to memorize these formulas, but I do want you to understand kind of where they're coming from and what they do. Similar to the population standard deviation, I use the Greek letter sigma. And again, it has a messy formula. Why does it measure an average or a spread of the data? Well, let's look at this x minus mu, or x minus x bar. X minus mu, you could think about as the difference between the data value and the mean. Square and square root makes it positive, so we really are talking about a distance from the mean. And adding them up and dividing by the total, that's an average. So that's why we can say this is, in a way, an average distance from the mean that the data values lie. Notice that the sample standard deviation has an n minus 1 in the denominator, and the population standard deviation has an n in the denominator. I don't care if you completely understand why you would do that. What I do want you to know is that they're different. So in a calculator, for example, it's going to have to give us sigma, the population standard deviation, and it will have to give us S, the sample standard deviation, because they will be different numbers. The mean, on the other hand, has the same formula whether you're talking about a population or a sample. So the calculator will only give us one number, and it will usually just say x bar, which will mean the sample mean, but also if you're talking about the population, it'll mean the population mean, even if it doesn't say mu. The variance is the square of the standard deviation. I will not get into what the variance is all about and how to interpret it. It's just a good number to know, and that's all I'll do with it. So here's an example. Okay, let's suppose that a biologist measures the height in meters of 6 giraffes. And the measurements were 5.2, 4.9, 5.4, 5.0, 5.2, and 5.5 in meters, by the way. Let's use our calculator to summarize this data, to find all of the statistics. So I do that. So here's the calculator. And I first need to enter the data. So I go to Stat. That's this button right here, S-T-A-T. And I want to edit the data values into the editor. So I hit Enter on Edit. Okay, so often your calculator will have other numbers in there. I need to clear them out, and here's how I do that. I go up to L1, and I hit the Clear button. Very important, never ever hit the Delete button. You will mess up your calculator, and it'll erase L1 forever, and unless you're really good with the calculator, you won't be able to figure how to get it back, and your calculator is ruined. You'll be coming to me crying. So don't ever, ever hit the delete button. Instead, use the clear button when you're in the editing mode. Then hit enter. And now I just type in my data values and hit enter after each one. So my first is 5.2. Hit enter. And then 4.9. Enter. And then 5.4. Enter. And then 5.0. Enter. And then 5.2. Enter. and then finally 5.5. Enter. Now that I have all of my data values entered into the editor, I hit Stat again. I hit the right arrow to go to Calc, which is Calculate. And I only have one variable, and I want statistics. So I hit Enter on one var stats, or I could hit the number 1. Then I go and hit second 1, which will type in L1. And then I hit Enter, and I have my statistics. So notice it tells us that X bar is 5.2. So the calculator does not know whether we typed in a population set of data or a sample set of data. We have to understand that for ourselves. So for example, if these 6 giraffes were 6 randomly selected giraffes from Africa, then this would be a sample. And yes, X bar would be 5.2. If these 6 giraffes were all 6 giraffes at our zoo, and we wanted to find out the population mean height of giraffes at our zoo, then it would be mu is 5.2. Okay, sigma x and sigma x squared, I'm not going to do anything with in this whole class, so I'm going to ignore those numbers. So then again, if you're talking about population or if you're talking about a sample, it's read differently. If we're thinking about this as a sample of giraffes in Africa, then we use SX, which is S, which is the sample standard deviation, about 0.228 or so. If we're thinking about these giraffes as the population of all the giraffes at our zoo, then we use sigma x, which is the population standard deviation, and that's about 0.208. N was our sample size, or our population size, and that was 6. If I hit the down arrow, the minimum, or the shortest giraffe, was 4.9 meters. Q1 is 5. That's the first quartile. I will get into that later in this lecture, but for now, just know that in your calculator, you can get the quartiles by using one var stats. I'm only going to be doing the calculator once in this lecture, so just remember for later on, this is how you get the quartiles. MED does not stand for Club Med. This is the median, and the median was 5.2. Q3 is what's called the third quartile, and that's 5.4. And the maximum was 5.5. So the very tallest of all the giraffes was 5.5 meters tall. If I wanted to get the variance, I would have to go back to the standard deviation. And if I round to 1 decimal, I can get away with using either of these. It's about 0.2. And remember, the variance is the square of the standard deviation. So I have to type that in as 0.2. And I hit x squared and hit enter. And the variance is 0.04. So those are the statistics or the parameters, depending on whether we're thinking of this as a sample or a population. So let's go back to our PowerPoint. Here's the PowerPoint. And next I'm going to remind you again about what the standard deviation is. And I'll also go over something called the standard error. So the standard deviation I've already talked about, but I can't talk about it too many times. The standard deviation, I would say, is in the top 3 of the most important ideas of the entire statistics course. And the standard deviation is a kind of average distance that the data values lie from the mean. The standard error, on the other hand, is also very important, but it's something that we're going to spend a lot of time later on talking about. So today I'm just going to briefly say it, just to say that you've seen it once. So for a sample size of size n, the standard error, which measures the sampling variability of a statistic, is given by sigma sub x bar is equal to sigma divided by the square root of n. So again, just so you've seen it once, when we get to talk about this in a few weeks from now, you'll have seen it, and then we'll talk about it in detail and really go over what it means. The next topic is z-scores, which are actually very important. And what they do is they combine a value, the mean, and the standard deviation all in one formula that will help us really understand how unusual or how far a value is from the mean. And the z-score is defined with this formula. Z is equal to x minus mu divided by the standard deviation. And it tells us the number of standard deviations from the mean. So let me give you an example. So last quarter's statistics final had a mean score of 76% and a standard deviation of 5%, while the psychology final had a mean score of 84% and a standard deviation of 6%. If Juan scored 86% on his statistics final and 93% on a psychology final, which final did he do better on compared to the rest of his class? So clearly, Juan scored higher on the psychology final, but the psychology final was easier because it had a mean of 84, and the statistics final had a mean of 76. So you really can't say, well, 93 is higher than 86, so Juan did better on the psychology final. So this is the z-score, is a way of comparing two different scores or two different values that come from different sets of data. So let's use z-scores to compare. So for statistics, the mean was 76, the standard deviation was 5, and Juan's score was 86. So let's calculate the z-score, which is the observed value, 86, minus the mean, 76, divided by the standard deviation, 5. I put that into my calculator, and I got 2. For Juan's psychology final, the mean was 84, the standard deviation was 6, and Juan's score was 93. Let's put that into the z-score formula. So z was 93 minus 84 divided by 6, and I got 1.5. So notice that Juan's z-score for the statistics final was higher than Juan's z-score for the psychology final. So we can conclude that compared to the rest of his class, Juan did better on his statistics final than he did on the psychology final. So for example, if they graded on a curve, Juan's grade would be higher in statistics than in psychology, even though his score on the statistics final was lower than the score on the psychology final. So that's how we can use z-scores. Other examples, for example, I got 1,140 on my SAT exam. Now, if you know anything about SAT exams today, that would be a horrible score today. But my score on my SAT exam, my z-score, was about 3.5, which was actually a very, very high z-score. So compared to the rest of the people that took the SAT when I took it, I did really, really, really well. Okay, had that score been today, it would be terrible. But the z-score is what matters, and that's really good. So let's move on and talk about percentiles. Percentiles are another way of dealing with the fact that if you don't know anything about the raw score, you can talk about how high or how low it is. And the percentile is defined as taking all of the data and dividing it into 100 groups with about 1% of the data for each group. And the formula is that the percentile is the number of values less than the score divided by the total number of values times 100. And there are a couple important percentiles. The first is the first quartile. The first quartile, which we'll call Q1, we saw in the calculator, is the 25th percentile. The third quartile, Q3, is the 75th percentile. Notice there is no Q2, because instead of Q2, that would be the 50th percentile, but that's the median, and we just use the median for the 50th percentile. Finally, the interquartile range, which is denoted as IQR, is the difference between the first and third quartiles. So the IQR is used if you're presenting to a sophisticated audience that understands this stuff. And it really tells you what that middle 50% of the data is. So percentiles are great. Again, things like SAT scores. Percentiles are much better than raw scores because it'll tell you where you stand compared to the rest of the class. So my percentile on my SAT score was in the 99th percentile. I did real well on my SAT score. Especially, as you might guess, I did really, really, really well in math. English was just okay. It was good, but my math had like 99.99 percentile. So you know what that means. You'll also see birth weights given in percentiles. So, for example, if a child is born in the first percentile, then that tells you that child is very, very small and probably will have to go to the ICU ward and get really taken care of because that child's in danger at the first percentile. You'll see percentiles given in other places too, anytime where you want to compare that value to the rest of the group. The box plot is going to be a graph that describes all of the 5-point summary values. And the 5-point summary values are the minimum, the first quartile, Q1, the median, Q3, the third quartile, and the maximum. You can get all these numbers with a calculator using the one-var stats that we saw before. And to create a box plot, we're going to put horizontal bars at each of these values. We're going to connect Q1 and Q3 to make a box. And we're going to draw lines from the minimum to Q1 bars and from the maximum to Q3 bars to make the whiskers. Pretty hard to read this and get the idea. So let's do one. So let's suppose we have the 5-point summary with the minimum of 4, the first quartile at 7, the median at 9, the third quartile at 15, the max at 20. So I'm going to start by putting all these on a number line. So here's a number line with 4, 7, 9, 15, and 20 drawn on the number line. Then I'm going to draw vertical line segments above each. So above the 4, above the 7, above the 9, above the 15, and above the 20, I draw a vertical line segment. Then I draw my box. So the box connects the first quartile and the third quartile. So I connect the bottom of the box by connecting 7 to 15 at the bottom. And I connect the top of the box by connecting 7 to 15 at the top of those bars. Then I draw what's called the whiskers. So I draw my left whisker by connecting 4 to 7 in the middle of the bars. And I connect 15 to 20 in the middle of those two bars. and that's by box plot. Sometimes we also call this the box and whiskers plot because we have our box, which is the interquartile range box, and we have the whiskers that go from the minimum to Q1 and Q3 to the maximum. So the standout of the box plot is the box. That's why we call it a box plot. So very easily we can see what the middle of the data values are. The middle 50% of the data lies between 7 and 15. The median is 9. Sometimes you'll put a little dot at the mean because the mean's important. Sometimes you don't. Sometimes we will take the outliers and we'll put dots at the outliers and we'll draw a box plot for the rest of the data. But here I just drew a simple box and whiskers plot. The next sketch I want to talk about is a histogram. So a histogram is a bar chart that depicts a frequency distribution table that we talked about in the last chapter. So here's an example, number of units someone might be taking versus how many people took those number of units. A relative frequency histogram is a bar chart that depicts a relative frequency distribution table. So the relative frequency numbers you find by taking the frequency values, so for example 130, and divide by the total, which was 500 for the sample size. And if you take 130 and divide by 500, you get 0.260. And you could do that for each of the frequency numbers, and you get the relative frequency numbers. And I could draw a histogram of the relative frequency values. Similarly, we can talk about the cumulative frequency histogram. So the cumulative frequencies are the frequencies that occur at or below that value. So for example, there were 463 values at or below 179. So to find the cumulative frequency, we start out with the first frequency, and then we add up the first two frequencies to get the cumulative frequency of the second value, and we keep going. Notice that the last cumulative frequency value will always be the sample size, because the number at or below that value is just the total number of numbers. Then finally, the relative cumulative frequency histogram is a bar chart that depicts the relative cumulative frequency distribution table. To get the relative cumulative frequency, we take the cumulative frequencies and divide by the sample size. So for example, 284 divided by 500 is 0.568. So here's an example of a histogram. And this is actually a histogram of z-scores. I put this in to remind you about z-scores because they're so important. So this is the histogram that shows you the difference in height between fathers and sons, and it's a histogram of the z-scores of those differences. Notice a few things. One is we can look at the histogram and we can see that it looks pretty symmetric. It looks like there were a lot of z-scores near 0, not so many far away. That's typical when you're talking about z-scores. Also, if you wanted to find out what the lowest z-score was or what the closest z-score was to 0, you actually can't find that out. What you can say is that there were a lot of z-scores between 0 and, say, looks like 0.25. But you can't say if there was a z-score at, say, exactly 0.2. So you lose the data values when you draw a histogram, but you get the shape of the data really well. You can identify outliers pretty well, and you can also identify where the highest frequency happened. What you don't have so easily is what the standard deviation is. You can take a guess. We could say the standard deviation was probably somewhere around maybe 0.8 or so, because most of the data is between negative 0.8 and 0.8. So that would be a standard deviation. Notice that negative 4 would be a strong outlier. It's really far away from the rest of the data values. Probably negative 3, okay, would be a outlier. We've seen that before already. I want to talk about looking at the shape of distributions. So if you have a histogram where you have the highest frequency on the right, then we have a tail moving to the left, we're going to call that negatively skewed or skewed to the left. When you have such an instance, that tail is going to pull the mean towards the tail away from the median. So the median is over here. I'm going to call x with a tilde on it. And the mean, x bar, will be over to the left when we have a skewed left distribution. Similarly, a skewed right distribution means that the high frequency is on the left and the tail is to the right. Now that right tail here will pull the mean to the right of the median. On the other hand, if you have a symmetric distribution, and that means that we're talking about the left and the right-hand side looking the same, then the mean and the median will be the same. So let's next talk about modality. So remember, mode is the highest frequency value. If there's just one mode, like in this example here, where there's a one high bar and then low bars to the left and right, we're going to call that a unimodal distribution. By the way, we saw that skewed left and skewed right. Those were also unimodal, and so was that symmetric one we saw was unimodal. Bimodal means that it has two modes. And they don't have to be exactly the same height, but you have two tall frequency bars that are separated from each other. And that's a bimodal distribution. You'll see that, for example, if you're talking about gender. So often, if you're looking at, say, heights of men and women, you have kind of the men's typical height and the women's typical height. And that'll be very different from each other. You'll have two modes. Whereas unimodal means that you're not really taking from two different types of people or two different types of things. You're taking typically from one type of population, and you have that one big mode in the center, or the mode could be in the left or the right. If you happen to have more than two modes, we just call it multimodal. An important distribution I want to talk about is called the uniform distribution. A uniform distribution means that whether you're far left or far right or in the middle, the frequency's basically the same. So this occurs, for example, if you look at the number pi, you remember, was about 3.14. You might remember that. But it's actually 3.141592658, ... It goes on and on and on. If you looked at the first 3 billion digits of the number pi, and you do a histogram of those digits, it's going to look very uniform. The number of zeros and ones and twos all the way up to nines are all about the same frequency. So this, by the way, is a relative frequency histogram because I'm looking at the relative frequency. About 10% for each of the digits occurs for the number pi. The next distribution, which is the most important distribution of this entire course, is called the normal distribution. The normal distribution has some very important attributes. The first is that it's symmetric about its mean. So here's the mean, and we see the highest frequency is right here at the mean, and the left-hand side and the right-hand side are mirror images of each other. Secondly, it's a unimodal distribution. There is only one hump, and that hump does occur right at the center. And then finally, it's bell-shaped. So it looks like a bell. If you kind of draw what this histogram is, it looks like a bell. So this is an example of a histogram that is approximately normal. We'll get into this into much, much more detail later on. We're going to have an entire chapter just to talk about the normal distribution. And we'll find out later that normal distributions occur especially when we're looking at what's called sampling distributions. So if we're looking at all possible sample means from a population, they follow a normal distribution. If you don't quite know what I just said, that's okay. It won't be okay in a few chapters when that's all we talk about. So if we happen to have a normal distribution, we're going to have what's called the empirical rule, which says the following. 68% of the data values will have a z-score less than 1. 95% will have a z-score less than 2. And 99.7% will have a z-score less than 3. If you have an approximately normal distribution, then these values are approximately true. About 68% of the data have a z-score less than 1. So here's an example. Male black bears average 300 pounds. They're big, by the way. Okay, if you see a male black bear in the forest, respect that black bear. Keep your distance. Make a lot of noise so that black bear leaves because they're big and they're fierce. Their standard deviation is about 75 pounds. I'm not sure on that. I kind of guessed, but it sounded about right. Okay, let's assume that these black bears are approximately normal. Then what is the range for the middle 95% of black bears? So to find that, what we do is we take 300, that was the mean, and we subtract 2 standard deviations. So 300 minus 2 times 75, and that's 150. We also can take 300, and we could add 2 standard deviations. 300 plus 2 times 75, and I get 450. So I can conclude that the middle 95% of all black bears weigh between 150 and 450 pounds. They're big guys. If you don't have a normal distribution, you cannot use the empirical rule. That's really important to remember. In this class, the only way we're going to be able to decide whether we have a normal distribution is by looking at a histogram and saying, does it look pretty bell-shaped or does it not look pretty bell-shaped? We will have one other way, but that's much later, and I don't want to talk about it now. In advanced courses, there are very scientific ways of defining whether a distribution looks normal or not. If you don't have a normal distribution, you could still do something that's similar, and it's called Chebyshev's theorem. It's much weaker than the empirical rule, but at least it gives us something. And it says the following. At least 75% have a z-score less than 2. Notice that's weaker than saying approximately 95% have a z-score less than 2. Okay, knowing what percent is versus saying that it's at least a number is very different. At least isn't as good as knowing the number. At least 89% have a z-score less than 3, and at least 95% have a z-score less than 4.5. So notice that at least 75%, it could be 99%, which isn't even close to 75%, and that still would be true. So here's an example. The average miles per gallon of cars in the United States is 23.8, and the standard deviation is 6.1. At least what percent get between 11.6 miles per gallon and 36.0 miles per gallon? Here we're not going to assume that the distribution is normal, and because of that we cannot use the empirical rule. Instead, we use Chebyshev's theorem. So we can say that 11.6 is 2 standard deviations below 23.8. So notice that twice 6.1 is 12.2, and 23.8 minus 12.2 is 11.6. And 23.8 plus 12.2 is 36.0. So that tells us that we're within 2 standard deviations of the mean. And Chebyshev's theorem tells us that at least 75% of all U.S. cars get between 11.6 and 36.0 miles per gallon, because 11.6 and 36.0 is the low side and the high side of 2 standard deviations from the mean. Okay, next let's look at one more graph that we can use. This is called the stem and leaf plot. The stem and leaf plot is a chart in 2 parts: the large units and the small units. The large units are on the left, and the small units are digits that are placed horizontally on the right to form a number bar. This probably doesn't mean a lot to you until we do an example. So let's do an example. So here are the exam scores that happened in my last class. You can see they range between this person, probably didn't study, got 24%, not very good on the exam, and this person got 99% on the exam. A couple of them did, actually. And here's how we draw a stem and leaf plot for this data. First, we draw a t-table. So on the t-table, I'm going to separate this into its 2 digits. Well, we have 1's digit and 10's digit. So I put 10's digit on the left and the 1's digit on the right. Then I notice the 10's digit goes between 2 and 9. It does skip 3, but I'm still going to put that in. So I put 2, 3, 4, 5, 6, 7, 8, and 9 under the 10's digits. Then I'm going to look at the data values. I have a 24. That have a 10's digit of 2 and a 1's digit of 4. So I put a 4 for the 1's digit. Then I have a 42. Okay, I don't have any 3's for the 10's digit, so that gets left blank. But the 42, I have a 10's digit of 4 and a 1's digit of 2. For the 59's, notice I have a 10's digit of 5. Each of them have a 10's digit of 5. And the 1's are 5 and 9. So under the 1's, I put a 5 and a 9. For the 60's, I have a 3 and an 8. For the 70's, I have a 2, 5, 6, 7, 7, 7. So I put 2, 5, 6, 7, 7, 7 under the 1's digits next to the 10's digit of a 7. And I do the same for the 80's and the 90's. So notice that a stem and leaf plot gives us a shape of the distribution. We could tell right away that this is a skewed left distribution because it has a high mode on the right, or at the high value, and then it has a tail for the small values. So it's skewed left. It's also unimodal. But we could do more. With a histogram, you lose the exact values. With the stem and leaf diagram, I could tell you, for example, that there were 3 scores of 85, because under the 10's of 8, I have 3 5's. So I don't lose my data values. Sometimes I actually draw the histogram along with the stem and leaf plot. So here's my histogram drawn on the stem and leaf plot, and then I have it all. I have the histogram and the stem and leaf plot. I don't lose my data values, and I get the shape very well shown. Here's the issues of the stem and leaf plot. The first issue is that if you are showing this to an audience that doesn't like numbers, so they have that fear of numbers, then this will make them very fearful because there are numbers everywhere. So for a lot of people, they will consider this ugly and scary. So stem and leaf plots are given to audiences that don't mind numbers. Scientists love stem and leaf plots. It can scare off the math-phobic group. Another problem with the stem and leaf plot this worked great for a class of size 20 or 30. Imagine doing a stem leaf plot for the SAT exams of all students who took the SAT in America. That would not work because you have maybe 1 million people taking the SAT and you can't draw 1 million numbers on a piece of paper. Just isn't going to work. So this only works when we have a kind of tame sample size, a sample size that's maybe less than a couple hundred. But when you do have a nice tame sample size and you have an audience that doesn't mind numbers, it's actually a very powerful chart. Let's look at a few other charts that I'm not going to spend a lot of time on, but I do want you to at least be exposed to them. So this chart is called a Pareto chart. And a Pareto chart is a bar graph for qualitative data that is arranged in decreasing order. So here's an example. And this is an example. Survey question is, why did you break your diet? You've been on a diet and you're not anymore. What happened? Notice it is a qualitative survey question because the answer is, it was just too hard to diet, or I was bored and I just watch TV and I eat when I watch TV. Okay, whatever it might be. So this is a bar chart, but not a histogram, because histograms are representative of quantitative values, whereas Pareto charts are for qualitative data. We can see right away that cravings, I just felt like having that big half-gallon of ice cream. That was the number one reason why people broke their diet. On the other hand, being hungry wasn't very important. That was not what broke their diet. So you can see with a Pareto chart from highest to lowest really easily. The next chart is a pie chart, and you've all seen a pie chart before. I wanted to show you how you construct a pie chart. If you wanted to do this by hand, you calculate the angle by taking the relative frequency and multiplying it by 360 degrees. So a pie chart is just a circle graph such that the slice's angle is proportional to the category's frequency. So here's an example. This is a pie chart of the air. So in the air, most of the air is not oxygen, it's nitrogen. And about 79% of the air in our atmosphere is nitrogen. On the other hand, about 20% is oxygen, and the rest is other gases like carbon dioxide. Everyone talks about all that carbon dioxide in the atmosphere. Actually, there's not very much. Even in global warming, there's not very much carbon dioxide, but even a little bit will affect the atmosphere tremendously. So that 1%, although it's little, it actually is really important. And then the next diagram I want to show you, or the next chart, is called a frequency polygon. That's very much like a histogram, but instead of drawing rectangles, we just draw the dots at those frequencies and connect the dots. And that's it. Okay, so this is how many sweets people eat by how many people there are that ate that net number of sweets. So we can see that this was unimodal. Not quite symmetric, it's slightly skewed to the right, but close to symmetric. When you have real data, you're not going to get perfectly anything. You typically won't get perfectly unimodal or perfectly symmetric or perfectly skewed left or skewed right. So you say somewhat symmetric but slightly skewed is a typical way of describing data. Then the final graph I want to talk about is called a time series graph. A time series graph is a frequency polygon, but the horizontal axis represents time. So here's an example. This is a time series graph of violent crimes per 100,000 U.S. inhabitants from 1994 to 2013. So we can see very clearly that as time has moved forward, the violent crimes per 100,000 inhabitants has really gone down by a lot. So it may seem like things have gotten less safe, but that's actually not true at all. So be careful about having that feeling that it's gotten more dangerous. What you really need to do is look at the statistics. And only after looking at statistics can you see what's really going on. And our world has gotten safer and safer and safer as time has gone on. At least our country has really gotten safer. So you should feel good about yourself. Things are good. Okay? And if you look at 2014 and 15, it's actually even getting better. So let's hope for a wonderful world. This is the end of the lecture. It's always good to end on a positive note that things are getting better. So if you had any trouble with any of the topics, there were a lot of topics in this particular lecture. I don't think any were that intense. Make sure you fully understand the standard deviation, because that's the most important topic of the day. Then if you have trouble, especially with the standard deviation, please ask me. Or if you're in another class, ask your instructor, or ask your friends, or ask a tutor. Just get some help, look at this video again, and make sure you understand all of the topics, especially the standard deviation. And just to let you know, the next topic to talk about, the next chapter, is on probability, which is one of the most difficult chapters of this entire course. So be ready for a tough one. It's a lot fewer topics, but each topic can get you confused. So I hope you have a wonderful day or week or time, whatever you're going to be doing between now and probability, and brace yourself with some difficult times. So have a great one. Goodbye.